Okay. Morning, everybody.
Good morning.
Hope you've had a nice Saturday morning. Great to see you all back. Okay, so where did we leave off last time? We tried to have a look at very commonplace phenomena. We tried to peek under the hood of what happens, and I posed a couple of provocative and seemingly dumb questions. One of them that I asked is, what changes if you take a cold mug of water and you heat it up? How does the water differ? We asked about electricity. How many kinds of electricity there are? There's the one that comes out of the wall, there's the one that comes out of a battery. How are they related? And what we also asked is, about the structure of matter. So I told you in Illinois anyways, a lot of our electricity comes from nuclear fission. So it depends upon some very fundamental properties of what matter is made of, what this table is made of. And we asked about, how this relates to everything else. And, if this consists of atoms, what does electricity consist of? And so then this brought up the question that we are going to follow throughout the rest of this lecture series. And that is, how the hell did we get here? What brought us from this sort of gold bracelet from ancient Greece, 4th century BC, very intricate wires, gold wires, to something like this, which in the 1900s enabled radio communication for the first time. And we brought it up into three sort of sub-questions. The first of which we're going to start discussing today, and it will keep us busy for today and also maybe, next time. And that is, what is heat? That speaks to the first of my 3 bullet points from just before. So where to start? Mankind has lived with heat ever since antiquity. Okay, so maybe this is a good place to start. Let's go all the way back to antiquity, 70 AD, Egypt, Alexandria, big, prosperous, cultural high point of antiquity. And to this person here, Hero of Alexandria, he worked at what they called the Museum of Alexandria. By the way, this is where our current word for museum comes from. Museum today we associate with a place of exhibition, but back in the days, a museum was a lot more than that. It was more like a research institution. It had a big library. In fact, the famous Library of Alexandria was part of that institution. It was a place where people could explore their creativity and write and do research. Okay, if you translate it literally from ancient Greek, it means seat of the muses, so a place of inspiration, which I think is still a very good description of what a museum today is supposed to be. So anyways, this person, Hero, he was a mathematician, he was a physicist, he was also a writer and an inventor. And one of the things he wrote was a book where he collected all of his inventions. And he dedicated 1 page to each invention. Okay, and you open the book and you find many little gimmicks. And just to give you an example, here is one of them. There would be a title at the top of each page, and on the right-hand side he would put a sketch, and on the left-hand side he would put a description of how to build it and how it worked. Okay, so here's one of the things he came up with. Sounds produced on the opening of a temple door. Okay, so this is the sketch that he puts. And you can kind of appreciate how it works. There is the temple door, and there is some sort of pulleys and ropes and levers and such, and there is a trumpet, the mouthpiece of which is immersed in a pool of water. And now you can appreciate, if I open the temple door, that entire thing is going to start moving, and that trumpet is going to be submerged into the water. The trapped air is going to be pushed through the trumpet, and voila, you got your trumpet sound. What he also invented and published in this book is this: how to construct an altar such that, when a fire is raised on it, figures at the side shall offer libations. Okay, very elaborate title. But again, we can try to understand what he imagined. Okay, so here is the altar, the base of which would be airtight, and he would put water into it. Okay? Then you have your 2 figures, and you have these concealed pipes that run out and sort of reach and sort of come out at the ends of the figures, and then he put up a fire at the top of the altar. Now, of course, today we can sort of imagine what happened. There's trapped air inside this volume above the water. It's going to be heated by the fire on top of it. The air is going to expand. It's going to push onto the water from the top and push up the water through the pipes and out the hands of the figures. Okay, this is the first recorded usage of heat to do some mechanical work. Okay. But Hero didn't fully appreciate what he was really getting himself into. You can notice, for example, that here there's this pipe that connects somehow this air volume with the base of the altar and has this weird conical shape. It extends and then it goes back down again. And there's this one paragraph in his book that really shows that he didn't really understand what he was doing. So he writes, the pipe through which the heat is to pass, okay, this pipe, should be broader towards the middle, for as it is requisite that the heat, or rather the vapor of it, should expand and act with greater force. I have no idea what this means. Right? So clearly, there was some sort of heat going on, and maybe the heat sort of, went down the pipe, or it's rather the vapor of the heat, but what is the vapor of the heat, and so forth. Okay, so this shows us, and apparently he wasn't really troubled by his own ignorance. He sort of was happy with finding some makeshift argument for how this works to make it sound nice and to put that in the book. That was the very origin, that the first instance of somebody writing about heat that survived until today. There was somebody else writing about heat from a very, very different perspective in around the similar times, 140 AD, Galen of Pergamon. He was a physician, and he was an extremely, extremely prolific writer. It is said that he employed 20 scribes that would write down what he would dictate. And in fact, more than half of the literature that survives from that period is due to him. Okay, so he was, he wrote down everything that he could. And being a physician, he thought about how the body works, and he came up with this grand scheme of his. And he said there would be 4 bodily fluids. Okay, there would be choleric, or which he also called yellow bile, and that would be produced in the kidneys. There would be blood, of course. There would be melank, or black bile, that's produced in the liver. And there would be phlegm. Okay, these are the 4 bodily liquids. And they have to be in balance, because if they're out of balance, you get sick. He also associated those with a person's character. Okay, not only did they determine whether you're healthy or sick, they also determined how you were as a person. For example, choleric, that bodily fluid, we know today, and the expression for somebody being a choleric, right? Somebody who is very rash and easily excited. Blood, the sanguine, okay? Nice and easy and calm. Melank, the melancholic. And phlegm, the phlegmatic. So for him, there was a very clear connection between the bodily fluids that determine your state of health, but also a person's temperament. In fact, he also made a third connection, and that is with temperature. And in fact, this is where that word comes from temperament. Temperature, he says, if a person gets sick, they might develop a fever, they might develop temperature. So clearly, if these bodily fluids are out of balance, something's got to do with the temperature, right? Because if the balance doesn't exist, person gets sick, they develop a temperature. So, because of these 3 connections, temperature, on the other hand, should also affect a person's character, right? And so he writes about it in his book, and he speaks about the Celts and the Germans that live up in the north, because from where he was living, right? He was in Pergamon, which is present-day Turkey. So for him, Germans and Celts, they're up in the cold north, where it's cold and wet. And he writes, however much innate heat there is in their bodies, it would have fled for refuge to the internal organs, along with the blood, which here is agitated, confined in very narrow spaces, and seething, rendering them high-spirited, rash, and quick to change their opinions. He would also make statements about people living in the south, in the tropics, which according to him would be sort of lazy and slow and so forth, because the heat, would make them such. Now he himself, of course, he lived in a temperate region in Turkey where everything is super nicely balanced, and so he didn't explicitly write that, but it was very clear if you read between the lines that he thought of himself as living in sort of the best possible region on Earth, so that it wouldn't have to suffer from these temperature effects. So anyways, for him, it was all about the balance, right? These bodily fluids had to be balanced and so on and so forth, and it was only logical for him to come up with a way of measuring temperature, whereas developing a scale to measure temperature, because it was all about temperature. And so here's what he does. He starts from the hottest of all of those things that come to perception, for example, fire or boiling water, hottest possible things there are, and he puts that at the top of his scale. he also thinks about the very coldest of the things that we know, which for him was ice or snow. And he puts those at the bottom of the scale. And then he has a very important thought, and he says that somewhere in between there is a center point, okay, that you can imagine. There is some sort of continuum that connects the coldest possible with the hottest possible thing, and that center point is sort of equally removed from these two extremes. But then he says, this is not some sort of fictitious, neutral center point, but in fact, you can actually produce something. You can instantiate an object with that temperature by mixing together hot things and cold things, okay? Mixing an equal mass of ice with an equal mass of boiling water. That's, a very, very important thought. And because everything in his scheme came in multiplets of 4s, 4 bodily fluids, 4 temperaments, and so forth, also his temperature scale had a neutral point. It had 4 degrees of hot, it had 4 degrees of cold. And the most astounding thing to me is that nothing in this scheme really changed for 1,500 years. So if you look, in 1578, there was a person, Johannes Hasler, in Bern, in modern-day Switzerland, and he was also a physician. And he also wrote a book, a textbook if you want, an instruction book, that he called Of Medical Practice. Okay, this would be a book teaching people how to treat their patients. And you open the book, and there is problem number 1. Okay, in this instruction guide, what is the first problem you need to solve as a doctor examining a patient? And the first problem is to find the natural degree of temperature of each man as determined by his age, the time of the year, the elevation of the pole, and other influences. Okay, so he has still this idea of Galen in mind that a person's natural temperature depends on where they live, what their surrounding temperature is, and so forth. By elevation of the pole, he really means the latitude. Okay, so where on the globe they're living. And he furnishes the reader with this table that goes with problem number 1. And in this table, there you go, you have Galen's temperature scale. 4 degrees of hot, 4, 3, 2, 1 neutral, and then 4 degrees of cold going down. And then in the other column, you have the latitude of the patient. And you see if somebody is living near the poles, they're sort of, very hot, and if they're living sort of close to the poles, they are supposed to have a colder natural temperature. Okay, their body temperature is supposed to depend on where they live. Now, of course, you might say that's stupid. How on earth could he have gotten away with that? Right? How didn't he sort of think about measuring, visiting these people and measuring their body temperature and comparing the body temperature of different people in different regions? That would have shown him that this is just nonsense. Right? But that's sort of the irony here. He didn't have a way to measure the temperature. And, likewise, nobody else did, so nobody else could prove him wrong. Right? And isn't it sort of a natural idea that the surrounding temperature has some effect on the human physiology and on their internal temperature? I don't think it's super far-fetched. But at the same time, people just didn't know. And so we need to find a way to measure temperature. And the thermometer, or as people called it then, the thermoscope, is one of those weird inventions that didn't exist for a very long time and then suddenly, popped out without anybody knowing, who invented it. And it actually popped up almost simultaneously in various different regions of the world. There's south of the Alps in Italy that we're going to follow this story, and there's also a seemingly parallel invention of the thermometer north of the Alps in sort of Denmark and the Netherlands. But there was a very big Italian school that was centered on this person, Giovanni Sagredo, and he had a very colorful history. He was a mathematician in Venice, which today is a city in the north of Italy, but back then was the Republic of Venice, a very prosperous, independent state that got very rich due to trade. Okay, had a big harbor. He was sent to Syria at some point as a diplomat, which the Venetians had conquered 300 years before, but then he sort of spied on the Persians, but he was caught, and that put an end to his diplomatic career, so he was sent back to Venice. And this is where we're going to meet him, back when he came to Venice, in his sort of later stages of his life, because he was also a very close friend of Galileo's, the giant of science in Italy, and the two exchanged letters. And unfortunately, only his side of the conversation really survived. His replies that he got from Galileo, they got lost, but we know what he wrote to Galileo. And these letters tell us a lot, and it's wonderful to read, so I want to show them to you. So he writes to Galileo Galilei on June 30th, 1612. Senior Muller told me about an instrument of Santorio's, we're going to see who this guy Santorio is in a second, with which cold and heat were measured by means of compasses. And finally, let me know that this is a large glass bulb with a long neck. Okay, something like this. There's a large glass bulb with a little volume at the top that contains trapped air, the bottom of which would be immersed in a bucket of water, such that part of that tube is filled with water. Okay? In today's terminology, we will call this an earth thermometer, simply because the air that's trapped inside is the substance that measures the temperature. You can imagine, if it gets hot, like with the altar before, that air would expand and would sort of push the water line down. Similarly, if it got cold, the water line would move up. Okay, so on this first set of thermometers, cooler was actually further up and warmer was actually further down, exactly the opposite of what we know today. And he has this instrument, and he says, I immediately devoted myself to making some very fine and very elegant ones, because he was also very good with his hands. He wasn't simply a mathematician, but he was also a practitioner, a glass blower, and that's what he would do. He would work so fast in an hour, I can finish as many as 10 of them. He was clearly proud of himself at being able to make as many thermometers as he could. Then, the year afterwards, May 9th, 1613, he would write another letter. He says, by now, the instrument for measuring heat has been reduced by him to various very elegant and convenient forms. Okay, he was clearly experimenting with different ways of making these thermometers and how to make them work practically. And with those instruments, I found various marvelous things. For example, that in winter, the air may be colder than ice or snow, and that water just now, in May, appears colder than the air in similar subtle matters. Okay, suddenly, with this instrument, you can imagine him running around and putting it to all of the things he could find around him. He would find out all of those marvelous things, as he called them. And then he continues, I have clearly seen that well water is colder in winter than in summer, although our senses tell differently. Okay, when I first read the sentence, it gave me the goosebumps, because here's a person who, in cold winter with the wind blowing, you go to a well, you draw up water, and the well feels warm to you. Likewise, in summer, in the heat of summer, you go to the well, and the water is pleasantly cool. Although he says his instrument tells him the exact opposite is true. Now, who are you to trust? Imagine, put yourself into his shoes. Are you going to trust your own senses, or are you going to trust your instrument? I think it's a remarkable step that he puts the instrument over his senses, and he trusts what the instrument tells him, instead of telling the instrument is just wrong, something else must be going on. And so he continues his exploration with the thermometer. 2 years after, 1615, he again writes to Galileo. He says, 2 days ago it snowed, and he now starts to compare things. Here in my room, my instrument showed 130 degrees of heat, more than there was 2 years ago at the time of the very rigorous and extraordinary cold. Okay, so let's follow his letter. Here we have the thermometer. The room, he says, 130 degrees more than at the extraordinary and rigorous cold. So if we put that at 0, we're now 130 degrees above 0, okay, in his scheme. Then he continues. The instrument, immersed and buried in snow, showed 30 degrees fewer, that is to say, only 100. Okay, so his room was 30 degrees above the snow outside, which was only at 100. But then he says, immersed in snow, the thermometer, with salt, it showed 100, again, another 100 fewer. Okay, so snow and salt is again up here at the same level as the rigorous and extraordinary cold that he mentioned. And so he concludes, as the instrument has gone up 360 degrees in the greatest heat of summer, it appears that salt combined with snow up here increases the cold by as much as amounts to a third of the difference between the excessive heat of summer and the excessive cold of winter. So what he says is if I put cold at 0 and summer heat at 360, going from snow to snow and salt changes by 100, which is a third of going from 0 to 360. Okay, so not only does he trust his instrument, to tell him something that his senses negate, he also trusts his instrument to actually compare different temperatures. he starts to be quantitative in his measurements. And he says this is a thing so wonderful that he can provide no credible reason for it. He has clearly taken away, with his research. And this is, in fact, how most temperature scales today are defined, right? You have 2 reference points. He picked rigorous cold and excessive heat. And then you divide those two, the space in between, in a certain number of degrees, right? And this is how you measure temperature. That's not at the extreme, but that's it somewhere in between. Now, we mentioned this person, Santorio, and I should tell him who he is, because he is also a really fascinating person. He was the professor of medicine at Padua. And he was one of those people who measure everything, who don't take anything for granted, they measure it. And so, for example, he put up this weighing chair. He would weigh himself constantly for 20 years by sitting in this chair, and you can see this chair would be suspended from the ceiling. There's some weighing mechanism. And he would weigh himself, and he would monitor how his weight would change as he consumed food. And he would also do the opposite. He would also measure the weight of his excrements, and then he would discover that he would actually consume more weight than he would lose, and concluded that there is some energy being consumed in the body even if you just sit still and do nothing. That was the discovery of metabolism, right? That the body exerts energy and does something with the nutrition that you provide, even if you don't do any physical exercise. And so Santorio, as we already know, he also wrote about thermometers in the medical context. And he writes, I wish to tell you about a marvelous way in which I'm accustomed to measure with a certain glass instrument, okay, a thermometer, a certain glass instrument, the cold and hot temperature of all parts of the body. Okay, he doesn't measure snow and well water, he measures the temperature of his patients all over their bodies. And so exactly, he continues, that we can measure the degrees and ultimate limits of heat and cold at any time of day. Okay, he's very convinced about the precision of his measurements. It, the instrument, is in our house at Padua, and we show it very freely to all. Okay, he speaks about a thermometer. Keep that in mind. He puts it in his house, and he advertises everybody who wants to see a thermometer, they should come and visit him. And then he promises that a book about medical instruments that are not well known will shortly appear, in which we shall give an illustration of this instrument and describe its construction and use. Okay, he wants to make it wider available. He wants to write about a thermometer and how to use it in medicine. There was a time when thermometers in medicine were really not a thing. And in fact, these thermometers, these air thermometers, as we call them, they had a serious flaw that people up to now weren't really aware of. And that flaw is that this water bucket at the bottom is actually open. Okay? So that means not only does the temperature affect the water level by expanding or contracting the air that's trapped inside, but also the atmospheric pressure around can affect the water level, right? Because the atmospheric pressure can reach the water from the outside and also, do the same thing. And it was Blaise Pascal, 29 years after that first letter that we just read to Galileo from Sagredo, who pointed this out. He did many experiments that we could talk about for an entire hour if we wanted. And from these experiments, he concluded that, for example, there is a lack of certainty that this thermometer indicates the degrees of heat, contrary to common sentiment. Okay, he points out, look, you have overlooked something. Actually, this thing, sometimes the water inside the instrument, sometimes rises when the heat increases, and sometimes falls when the heat diminishes. Okay, it does exactly the opposite of what you would expect. And in fact, today we know why that is the case, right? If you have a fair weather front, the air pressure rises, the temperature rises too, but if the pressure rises is stronger, it will push the water up. And if there is a low pressure front, a storm approaching, temperatures fall, but also air pressures fall, and then the water will fall because now that trapped air pushes the water down. Here is Blaise Pascal, and he was doing many other things, not related to thermometers or barometers. He actually went up a church tower in the mountain to prove that the ambient pressure depends on the altitude above the ground. He did many other things. He also invented computers, among others. So he was really a genius and a polymath. And we could talk for a long time about him. So there was this flaw that he pointed out, and that in fact he used not to measure temperatures, but to measure the atmospheric pressure. Okay, he took a flaw and turned it into a virtue, if you want. But we're interested in measuring heat and temperature, and so we should find a way to remedy this flaw. And just as with the invention of the thermometer in the first place, how this flaw got removed is not really clear, other than it's suddenly somebody figured it out without even knowing. And this person who figured it out was a physician in the French countryside, okay, a small village in southwestern France, Le Buc, far away from the big cities, Jean Rey. And he got a letter from a monk in Paris, Marin Mersenne. Those of you who care about prime numbers, might find this name familiar, because that's also what he is well known for. He wrote a letter to him, 1631. Okay, that was before Pascal pointed out that this flaw is actually there. And he writes about other things, but somehow, somewhere in his letter, he puts a side note where he writes about thermoscopes. And he says, the thermoscope, making the liquid descend by the rarefaction of its air, bears witness that heat makes air more subtle. Okay, we need to translate this. When he says that the liquid descends, okay, he means what he says, by the rarefaction of its air, which is the air above here, and if air is rarefied, it's sort of made less dense, and that means it expands. Okay, and he shows, and he knows how this thermometer works, because it bears witness that heat is actually at the cause of this. Okay, heat makes the air more subtle, and it rarefies because it expands and it pushes the water down. So he knows exactly how this thermometer works. But then Jean replies to Marin that, okay, hang on, I don't really know what you're talking about, because there are a variety of thermoscopes, or so it appears, because what you say cannot really agree with the one that I have, which is nothing more than a little round file with a very long and slender neck. Okay, so Jean also has a thermometer, but it doesn't fit the description in the letter. He says, my thermometer looks something like this. There is no open water bucket, no nothing. But to use it, I all fill but the neck with water. Okay, you have a closed file with some water volume at the bottom. There is again some water line because you don't fill it all the way up, and that's it. Okay. The heat expanding the water makes it rise more or less according to whether the heat is great or small. So now suddenly, independently and not knowing of his advantage, he invented what we have today as a liquid thermometer, where it's not the air that sort of expands and contracts, but it's rather the liquid that pushes up or down, and now warmer is actually up and cooler is actually down. And this thermometer doesn't have that disadvantage because it's hermetically sealed, the ambient air has no way of getting into it, and changes in air pressure do not affect the temperature reading whatsoever, but he was not aware of that advantage. And so, over the years, thermometry really became a precision science. There was a big school in Florence in Italy who constructed more and more elaborate of these liquid thermometers to make them more and more precise. And so the question was, now that we know how to measure temperature, what should we put as a scale, right? What are the units in which we measure temperature? And as we've seen before, all you need to do is pick an upper reference point, a lower reference point, and decide on a number of degrees in between. And so we've already seen the first of those. Sagredo had the lowest point set at the most severe winter cold, and the upper point at the greatest summer heat, and had 360 degrees in between, because to him it was some sort of compass, and a compass also has 360 degrees. But then other people had different ideas. A few years afterwards, his successors in Florence, they still used the greatest summer heat, but they used melting snow. That seems a bit more stable as the lower reference point. Later on, people took melting snow and said that's minus 10 degrees, and they took melting butter and said that's plus 10 degrees. Then people used freezing water and called that 0 degrees, and they used water that's boiling and called that 12 degrees. And that's still later in the 1700s, people used ice and water, that colder mixture that we already know, and called that 0 degrees. And again, that used boiling water, but now at a constant, well-defined pressure, and called that 60 degrees. And then finally, there is Fahrenheit in 1717, who used ice and water and salt in a very, very precisely defined mixture, and called that 0 degrees, and ice and water without the salt, and called that 32 degrees. And of course, that's still what we use today. But you can see it's totally arbitrary. To some degree, it's a matter of convenience. To some other degree, it's a matter of how precisely you can produce these reference points, because that depends on whether other people will be usefully able to replicate your scale and measure things that they can then compare with yours. So now we have explored the science of how people determined that there was temperature, how they even invented the fact that there has to be a way to measure temperatures, to compare temperatures, and how they could do so reliably. But now we need to jump onto a different storyline for a bit and look somewhere else. And that will be a storyline that's mainly circling around engineering. And that will be a storyline set in England, south of Britain. Okay, we leave Italy, we go to England, and we go to this person, Thomas Savery, or Captain Thomas Savery, because he was a military engineer in the Royal British Army. He had the rank of a trench master. But that's not why we are interested in him, because he was also a big hobbyist. So after work at home, he would, doodle with things, and he would invent, certain objects, among which was this one, his first invention, the one he was proud of, and it's the following. He wrote a pamphlet that describes it, and here's the title: Navigation Improved, or The Art of Rowing Ships of All Rates in Calms with a More Easy, Swift, and Steady Motion Than Oars Can. Okay, according to him, this is a different way of propelling a ship. Instead of rowing the ship, you do the following. You put paddle wheels on either side of the ship that would then propel the ship forward if they can be made to turn. But how can they be made to turn? By having people walk in circles on the deck of the ship and sort of bring some machinery into motion that would then spin the paddle wheels. Okay? And you can see in this pamphlet that he published, he was really intent of selling himself and selling his invention, because there would be a description of the engine. Here's the sketch that performs this feat. And there would also be the author's answers to all Mr. Dammer's objections that have been made against it. Okay, so he anticipates that people might not really like his invention for a couple of reasons that we'll see shortly. And he puts up preemptively a dialogue between himself and a naysayer, where he sort of tries to counteract the arguments against his invention. In fact, he built a prototype. He ran it on the River Thames in England. And he also pitched it to the Royal British Navy. They might consider using this to propel their ships. And he came in front of a commission, and there was the surveyor of the Royal British Navy who was the chair of that commission, and he wasn't really impressed. Because he says, this is his remarks, as far as we understand them, have interloping people that have no concern with us pretend to contrive or invent things for us. Right? So he says there are these random people that just run around and they want to be useful, but they are not really useful, because this thing actually doesn't really work in practice, and we'll stick with our sails and with our oars. So his first invention didn't really work out. He wasn't deterred and tried again. His second invention was a steam pump. In fact, he took out a patent for that steam pump on the 2nd of July, 1698. Here's the title of the patent. He patents a new invention for raising of water and occasioning motion to all sorts of millwork by the impellent force of fire, which will be of great use and advantage for draining mines, serving towns with water, and for the working of all sorts of mills where they have not the benefit of water nor constant winds, to hold for 14 years with usual clauses. Okay, so he says there is this universal machine that can run anything. It can pump water, it can do whatever you want. Wherever there is no supply of water, so you could put a water wheel, and there is also no steady wind, so you could put up a wind turbine. And again, steady to his way of doing things, he published another pamphlet. Right around the time, when some of those developments about temperatures happened before, which he wouldn't have been aware of. He was really a practitioner. He didn't sort of care so much about the quote-unquote academic way of defining different ways of measuring temperature. He was interested in selling his invention. And he called that the miner's friend, because it's an engine to raise water by fire. And then he goes on. And again, he would have these dialogues, these fictitious dialogues between him as the inventor and proprietor of this invention and the miner. And he would try to sell it to them. And he would have these wonderful illustrations where there is the miner with the miner's pick, and there is him holding the pamphlet, and the miner is clearly a bit depressed and so forth. And he claims, he really boasts the abilities of this thing. The force used in my engine is in a matter infinite and unlimited. Here we'll see shortly that's not true. And he also claims that it will raise your water 500 or 1,000 feet high, where any pit really so deep. Okay, there's no limits to what his invention can do, and you can see at the end the miner is really happy, and they actually make a deal. And so presumably, that was followed up by an installation of his invention in the mine. So what is this marvelous invention that he made? Let's see how it works. Here is that original sketch that he had in his pamphlet, and it looks a bit complicated, but we're going to go through it, and actually it turns out to be rather simple. there is a pipe at the bottom that would be the water intake pipe. Okay, that would sort of be down in the mine. This is where the water needs to be pumped up, and there would be likewise a pipe that would push the water up at the top, okay, up the mine shaft. There would be a coal fire somewhere, because the invention used the impellant force of fire, and it was fired by coal. And there would be a boiler where the fire would heat the water, would produce some steam. Okay, and there was a secondary water reservoir up here at the top that we'll see shortly what it's used for. And at the beginning, there are a couple of valves, okay, that shut off at various places, either the flow of the steam or the flow of the water. So now how does this thing work? At the beginning, you open the steam valve and you let that big empty pumping vessel be filled with steam. Okay? Hot steam brings up everything to a large temperature. Then you open, you close it again now that the steam is inside, but you do connect the intake pipe to the pumping vessel. And just doing that, nothing will happen until you open that valve up here in that water, auxiliary water volume. The water would come down, would rouse that pumping vessel from the outside and cool it down. And because that thing is now shut off from the boiler and everywhere else except the water intake, that steam would condense, it would cool down, and there would be nothing to fill it except the water from the bottom, and that's why the pumping vessel would be filled with water. Okay. So now you have performed one part of that pumping cycle. Now all you need to do is sort of push that water volume up the top. And it does that by opening that valve that connects the exhaust pipe and by opening the valve at the steam again. So now the steam would come in and push out the water through that pumping vessel up the top. Okay. This is how a steam pump works, but unfortunately, it never really became a miner's friend as he had envisioned, for the mere fact that it was very, very unreliable. In fact, that second stage, where you push out water at the top, relied on extremely high pressure steam, because at that point it's really the force of the steam that has to push up that entire water tube. And the mechanical engineering of the time wasn't really up to that level of reliability. People couldn't simply build steam boilers that could withstand such big pressures. And so it was very prone to explosions, which is not a really good thing if you put it down in a mine and it explodes, and the miner weren't really happy about it. So at the end, the bottom line is that it was used in two places, none of which were in mines, but in two London waterworks. Okay, where you could put the machine up on the surface, you would pump out the water from a well, and then you put it up in some water tower from where it would then distribute it across the city. So much for Captain Savory. There is another person who, around the same time, had similar ideas. And that person was Thomas Newcomen, who was an ironmonger in the southwestern part of England, in Devonshire. And we don't really know much about him, nor about his life, so he's a bit of a phantom, a bit of a hidden character. Much of what we know about him is through the records of an engineer from Sweden, Martin Triwald, who came to England to learn about the industrial methods that had already been in place in Britain at that time. And so he met Thomas Newcomen, and he writes that there is a man in Dartmouth, this is the village where he lived, and this is the house where he is thought to have lived with his family. There is this man from Dartmouth who didn't know anything about Captain Savory or his speculations, but who had also made up his mind to invent a fire machine for drawing water from the English tin mines. And that made sense because Devonshire at that time, and still today, and for a very long time before that, was a region with a lot of mining. There was a lot of metal ore to be extracted from the ground, and he, being an ironmonger, he would regularly go to those mines and supply metal and other parts that they needed to operate the mines, and he would witness how arduous the work was that these people had to do of lifting up the water from the mine shafts. And they would rely on horses and all kinds of manual labor, so it was natural for him to conceive of a better way of doing it. And so Triwald writes that for 10 consecutive years, Mr. Newcomen worked at his fire machine. Okay, and he would work on that fire machine with his assistant, with whom he ran his business in their spare time, because obviously they had to keep their business going. And so here is a sketch of what Newcomen in the end came up with. Newcomen's atmospheric engine, as it came to be called. We will see in a second why it's called an atmospheric engine. But at the face of it, it looks rather similar to what we saw before in Savory's story. There is again some coal fire, there's a boiler that produces steam. But now, instead of having a vessel that's sort of filled and depleted of water, and that would be the action of the pump, there would now be a drive shaft that would go down the mine and sort of mechanically operate a pump that could sit down in the mine. And so all the machine was doing is sort of drive that shaft and move it up and down. And to do that, he put up a piston. Okay, so there's this big piston up here. And here's the machine. Here's how the machine works. It works in a very, very similar way. You fill the piston with steam by opening the valve that sits on top of the boiler, at which point this counterweight here would sort of, put down the drive shaft, the other side would come up, the piston would extend, and the entire volume of the piston would fill with the hot steam. At which point you close the steam valve, you open that second valve that would again, let cold water into the piston, would cool down the steam, would condense the steam, would reduce the volume, and then suddenly it's the atmospheric pressure from the outside that would push the piston down, the head of the piston down, and up would come that drive shaft. Okay, this is why it's called an atmospheric engine, and it results in this up and downward periodic movement of the drive shaft. And the big advantage it had over Savory's machine is that there is now no need for high pressure steam that made Savory's machine so unreliable and prone to explosions, for the simple fact that the steam could be at atmospheric pressure. All you need to do is sort of slowly fill that piston, and in fact that would be aided by this counterweight pulling the other side down, so you don't have to do a lot of really high pressure steam work. But then also the upward, the actual pumping motion would only be done by the force of the atmospheric pressure outside. So again, you would not need any high pressure steam, which made this much more reliable. And in fact, he tried to put it to the market. But unfortunately, Savory's patent was still active, and if you remember, he patented all sorts of applications for his fire engine. So all Newcomen could do is really partner up with Captain Savory and use his patent and sort of share the profits with Captain Savory. And so here is the first steam engine that they put up at Dudley Castle, and you can see invented by Captain Savory and Mr. Newcomen. Savory invented none of that. He just sort of came along for the ride because he held the patent. And it was erected by Mr. Newcomen in 1712. And in fact, the Newcomen engine did catch on, and it did spread very, very rapidly. Okay. Machines were put up in Belgium, in the Netherlands, in England, and you can see that these were really building-sized large machines. And you can see there is the drive shaft that would sort of come out a window at the side of the building. It would go up and down, and then there would be a well down to pump up the water. You can see it here. And so by 1800s, 80 years after Newcomen invented it, around 1,500 of these machines have been built. Okay, that was a massive industrial uptake. And this is what led to this scenery. Okay, the early industrial revolution was extremely reliant on that coal-powered machine, which, as we're going to see, was extremely inefficient, but it was still a workhorse because there was nothing else that could do its job. It would be applied in coal mines and blast furnaces, anything where you needed, up and down motion like that. And in fact, it was so important that it not only changed the scenery to that sort of dystopic picture you can see there, it even found its way into poetry. So there was the great William Blake who wrote this poem. And did the countenance divine shine forth upon our clouded hills? And was Jerusalem builded here among these dark satanic mills? Okay, the dark satanic mills are exactly what you can see here, and they are dark and satanic because the smoke of burning coal is not really pleasant to inhale, and the fact that it was so inefficient was really the reason why there was so much pollution at the time. That was what engineering was doing at the time, and as we saw, none of those people, neither Captain Savory nor Thomas Newcomen, were really following all of that scientific developments about temperature and so forth. They were really hands-on people. None of them did that for a living. It sort of spun off as a side adventure. Savory was that hobbyist. Newcomen was an ironmonger, but they could put their hands to work and they could achieve something. But as we're going to see, it will take us a step back into science to really push the steam engine in that form to its limits. And the person we need to talk about in this context is Joseph Black. He was a professor of anatomy and chemistry at the University of Glasgow in Scotland. Okay, at a time when Newcomen's machine was already well established and was already widely used. And you can see there is a thing here, anatomy and chemistry. He was a doctor, first and foremost, because studying medicine at these times was really the entryway into science. Okay, medicine had existed for a very long time, and it was what people did if they wanted to pursue a career in research. So this is what he did. But he would work as a physician serving Glasgow and the surrounding towns, but it was never really his passion, and that's why he would also do, on the side, he would ponder things. And he was an extremely attentive observer, and we're going to see multiple indications of that. He was also extremely shy and didn't really write himself about what he discovered, even though it was very, very justified to write about it. And so much of what we know about him today and about how he approached his findings is due to lecture notes published posthumously by friends of his who thought it important enough that these things be written down. So what did he do? He had the following thought. If we take 1,000 different kinds of matter, at different temperatures, you could have a hot cup of coffee and a cold stone, or whatever you want, and you put them together in a room without a fire, with no windows, no nothing, you just put 1,000 different kinds with different temperatures into that room, and you wait. And after you've waited for a long period of time, and then you apply a thermometer to all of those objects in succession, you would find that the thermometer would give precisely the same reading. So he thought, and everybody of you will be able to relate to that at some point that hot coffee mug will have cooled down to the temperature of the room, right? And here is just the room without a fire, so that everything just cools down. But it would cool down, and that's the important part, to the same temperature. And he would call that an equilibrium, because this is what you end up with at the very, very end. Now I should point out that this is not actually that obvious. And in fact, having a thermometer available to precisely measure these temperatures of different objects was crucial for him to make that observation. Right? Imagine if you touch a piece of metal, it might feel colder than if you touch a feather, right? Or a piece of cloth, even though they might be at the same temperature. Right? So just, again, relying on your senses is not enough. You need to have an instrument to measure it, and the thermometer at that point was that instrument that he needed. So he goes on, I call this situation, where everything is at the same temperature, I call it the equilibrium of heat. And he continues that the nature of this equilibrium was not actually well understood until he pointed out a method of investigating it. So it's true, he gives himself credit where credit is due. People did not appreciate the importance of that equilibrium until he made that point. In particular, he quotes this colleague of his, Dr. Boerhaave, who was also a physician, we're going to see him in a second, who wrote the following. In equilibrium, there is an equal quantity of heat in every equal volume of space, however filled up with different bodies. That was Boerhaave's interpretation of what happens in that equilibrium state. There is the same amount of heat everywhere in space, irrespective of what the material is, irrespective of what the body is that occupies that space. The reason is, to whichever of these bodies the thermometer be applied, it gives the same reading. Now we need to be cautious here, because what he means by heat is not in the sort of colloquial sense of great summer heat, but it is something that is inherent to a body if it has a certain temperature. If we touch something and it's warm, we say it contains a certain amount of heat. Or Boerhaave thought of that as containing a certain amount of heat. And he would say that in this equilibrium, every object, no matter what, would contain the same amount of heat per volume. So here is Boerhaave, Dutch physician, again, chemist and botanist, who, together with Santorio, the guy with the weighing chair, was one of the founders of physiology. So that was, Boerhaave's opinion and part of the general consensus at the time. But Black points out that Boerhaave is actually taking a very hasty view of the subject and that he misses important clues. So here's what he observes. He writes about Boerhaave that he's actually confounding two things. He's confounding the quantity of heat in different bodies with the intensity of that heat, and that is the temperature. though it is plain, he says, that these are two different things and should always be distinguished. So here's an important part. Is it really that plain? Right? And it's crucial because people had thermometers, and thermometers measured temperatures. But then Black says, a temperature is not really the same as that content of heat inside a body. And that content of heat, you had no direct way of measuring it. Right? This is why this was sort of an important leap that Black made. Temperature is measured by a thermometer, but if that hot mug of coffee cools down to the temperature of the room, it's not temperature that flows out, Black says, but it's heat that flows out of the coffee mug. But Boerhaave said, these two things are the same. There is the same amount of heat in all of those bodies, but there's not the same temperature. Or he rather uses the fact that they have the same temperature to infer that there is the same amount of heat, which Black disagrees with. And the way Black substantiates his claim is really marvelous. He doesn't do any experiments by himself. He simply observes experiments done by others before that. And in fact, he points that there is this experiment that Fahrenheit did that was actually described by Boerhaave in his book, and that Black now interprets. Okay, he uses sort of Boerhaave's own writing against him in a sense. So what did Fahrenheit do? He did the simplest possible thing he could imagine. He mixed warm water with cold water. Okay, imagining the following: you have a certain volume of hot water at 150 degrees Fahrenheit, and you have the same volume of cold water at 100 degrees Fahrenheit, and you mix them together. And what you will end up with is lukewarm water, okay, at 125 degrees Fahrenheit. So much for a description of the experiment, but now Black says, and that's the crucial way of explaining it, or of interpreting it, that because you have 125 degrees Fahrenheit at the end, that hot water, which was 150 before, has cooled down by 25 degrees, while the cold water, which was at 100 before, has been warmed up by 25 degrees. Right? So that's why you meet in the middle at 125. Then Fahrenheit continues. He does the same thing, but now he mixes warm mercury at 150 Fahrenheit with, again, cold water at 100. And he sees what happens. Okay, you agitate it, you have to stir, vigorously, because the mercury is not going to dissolve in the water. It will sink down to the bottom. That's why you have to stir it to make sure it gets into this equilibrium state. But you would find at the end that it sits at 120 Fahrenheit. Okay, so now Black says, well, that's interesting, because now the mercury, which he called quicksilver, that was at 150 before, has cooled through 30 degrees, so it ends up at 120, while the water that started out at 100 only warmed up by 20 degrees. Okay, now there's a difference. And he says, just as before, it was the hot water that warmed up the cold water, and it was the cold water that heated up, was warmed up by the warm water. Here it's the same, right? It's the cold water that was heated up by the mercury, because the mercury gave off some of its heat, and the cold water absorbed some of that heat. And he says the quantity of the heat which the water has gained, and the mercury has given to it, is the same. Well, it's exactly the same as the mercury has lost. Okay, the mercury gives out some heat, the water accepts that heat, and as a result, the temperatures change. But the amount of heat that the mercury gives off is the exact same as the amount of heat that the water accepts, because you just agitate it, and everything stays inside your pot. And then he points out there is another experiment done by a certain Dr. Martin, who was also in fact a physician. Okay, you see many people were doctors at that time, because temperatures in medicine have been related, as we saw from the very, very beginning. And he did the following. He had a fire, and he again had mercury and water, equal volumes, and he put them at equal distances from the fire. Okay, so they would both be heated up. And he would find that the mercury, again the quicksilver, again as he called it, was warmed up by the fire almost twice as fast as the water. Okay, that's also interesting. And in fact, to Black, that was a hint in the same direction. Remember before, in Fahrenheit's mixing experiment, the quicksilver cooled through 30 degrees, while the water only heated up through 20. So, Black says, in some way, mercury reacts faster to heat than water, okay, in both of those scenarios. It's heated up quicker by the fire, and here it's sort of cooled more than the water is heated up. And so that's not obvious. Right? Again, as Black was fond of pointing out, it's not obvious because mercury, in fact, weighs 13 to 14 times as much as the same volume of water. So here is something that is much heavier, but then reacts much quicker to heat than the water. Right? It's a bit So here's what he then went on doing. He turned this into a more controlled situation. Okay? You have that substance that you want to test, you put a thermometer into it, and you put it at a certain distance from a fire that burns steadily. Okay, so it gives off a constant stream of heat. And then, you let it sit there for a very well-defined period of time. You said, okay, 10 minutes, I'll keep it there, and I will measure by how much that temperature has changed in those 10 minutes. Okay? And then he says the following. There is a certain amount of heat that the fire will have provided to my substance in those 10 minutes. Okay? And I will call it a sensible heat because I can sense with my fingers the effect of that heat. It will have warmed up, my water. I can feel it with my senses. And that sensible heat, how much sensible heat has gone into my substance depends on two things. It depends on how much that substance has been heated up, and it also depends on how much of that substance I put there. Okay? In other words, he says, if I want to heat up twice as much stuff, I need twice the heat. And if I want to heat up that stuff by twice the amount, I want to double the increase of the temperature, I also need twice that amount of heat. Okay? But he makes that precise in that way. And sort of this weird sign here just means that everything else being the same, doubling the amount of matter or doubling the temperature increase leads to a doubling in the heat that is necessary to achieve it. Okay, it's not a precise calculation, but he says, if I don't change anything else, this is what will happen. I need to double the amount of heat if I want to double the temperature increase or if I want to heat up twice as much. And then he points out, if I do change something, namely I put a different substance there, I put quicksilver or mercury instead of water, this doesn't hold anymore. We just saw that the quicksilver heated up twice as fast, right? So there is something else that other people have missed that depends on which substance I put. And he calls it the capacity for the matter of heat. Okay, so there is something that is inherent to the body that determines how much heat it can absorb before its capacity is sort of exhausted, if you want. Or, put in a different way, if heat is injected into something by putting it close to the fire, the temperature will increase. But if the capacity of that object for heat is higher, then the temperature will have to increase by less if the same heat is put into that object. And so he goes back and says, okay, well, in Martin's experiment here with the mercury and the water, we already knew that mercury is 13 or 14 times heavier than water, but it was nevertheless heated up twice the amount, okay, in the same time. That means the capacity for the matter of heat of mercury, is 26 to 28 times smaller than that of the water, because it's 13 or 14 times more matter, but it still heats up twice as fast, okay? So that's the number he arrived at, and it's very, very close to what we have today, which is 30 times. Okay, he was really close. And that's Black's first big contribution. The fact that there is something that depends on the material to describe how it reacts to heat. Okay? But now he continues and he says, well, let's see where this leads. And here's another experiment that he conducted in his head. Assume that you have ice cubes and you assume they have water. Okay? If you sit just below the freezing point of water, 32 Fahrenheit, you will have the ice cubes. If you sit just above that freezing point of water, you will have water. Okay? So there is ice at 32 Fahrenheit, and there is water at 32 Fahrenheit. So according to my experiment, I just need a minuscule amount of heat to go from ice to water. Right? The temperature literally doesn't change. Right? I can just go a tiny step above the melting point, and I will have water. But he says, well, hang on a second, if that were really true, I just need to touch an ice cube, whoop, and it would suddenly be water, right? Because the heat that I supply by touching it with my finger is minuscule, because all I need to do is just change the temperature of the ice by the smallest conceivable amount. And he says that's not really true. And he has this marvelous, picturesque way of describing it, because he looks around in nature. And he says, if this were really the case, that if I touched an ice cube, it would suddenly turn into water, the consequences would be dreadful, okay? Because if the ice and snow were to melt suddenly, the torrents and inundations would be irresistible and dreadful. they would tear up and sweep away everything, and this so suddenly that mankind would have great difficulty in escaping from their ravages. Okay, he says in spring, when all of the snow and the ice melts on the mountains, which it does do, but very slowly, if it were to melt suddenly, in the sense of me touching the ice cube and it evaporating into water, it would be incomparably more destructive. And so he says, what I just pointed out, in terms of the sensible heat that I need to use to change the temperature of something, there is also another type of heat. Because if I have ice or any other substance and I melt it, it somehow needs to receive a much larger quantity of heat than what I can measure with my thermometer. I put my thermometer into ice, 32. I melt the ice, it still reads 32, but I had to inject a large amount of heat, without measuring anything with my thermometer. Okay, so not only does the thermometer not measure heat directly, there's also something that the thermometer is totally blind to. And this heat is the thing that I need to add to give it the form of a liquid. So if I put my finger on an ice cube, I need to keep it there for many minutes. It's because I need to supply that different type of heat until the ice has totally melted. And that new type of heat is not sensible heat because I don't see it as a change in the temperature, and Black called it the latent heat. It's sort of hidden from the view of the thermometer. It's latent. And he says, well, with boiling water, it's exactly the same. There's the same peculiarity when I boil water. I can have hot water just below the boiling point, 212 Fahrenheit. I can have steam just above the boiling point, 212 degrees Fahrenheit. If, again, that water sort of evaporated suddenly into steam, it would be an explosion that had a violence equal to that of gunpowder. And yet, you're there in your kitchen, you boil water, it sits peacefully there bubbling. Right? So again, there is the same phenomenon. There is a lot of latent heat that needs to go into the water without changing its temperature to turn it into steam. So these are Black's two great results. On the one hand, the fact that there is sensible heat, that there is something that I need to put into a body to make it change its temperature, and the temperature changes in a proportion with something that is inherent to the material, its capacity for the matcher of heat. And then there is more than one kind of heat. There is sensible heat and there is latent heat, and I need both if I want to explain what I see around me in nature. And so here we are, and we have already come a pretty long way, like from something that people didn't understand and didn't grasp. At the beginning, there was this altar with the vapor of heat and so forth, some wishy-washy arguments. There was temperature being invented as a concept and related to the temperament of a person. There were the first people who built thermometers, but they were air thermometers, and they also measured the ambient pressure until somebody, by accident, as we saw, discovered that you could have a thermometer that doesn't measure the ambient pressure. Thermometry became a real precision science, and in parallel to that, we had the engineers that weren't aware of any of this. They started, building stuff, steam engines. There was Savory and there was Newcomen, and that led to the early part of the Industrial Revolution. And then we switched back to science, and we saw that, okay, with a thermometer in your hand that you could trust, you could actually learn a substantial amount. By putting things together in a room, letting them cool down, by mixing substances, and observing precisely what happens. And then eventually, we found that there are these two different kinds of heat, latent heat and sensible heat. So heat has suddenly turned into a lot more of a subtle concept than what it appeared at the beginning. Something that was simple and sort of intuitive because you could touch warm objects and you would feel them, has turned into a quantitative but also more subtle piece of science. But we did not really address the question of what is heat. Right? We had seen people find different ways and different handles of measuring it, but they didn't really come anywhere close to answering the question of the origin that sits behind that. And this is where we will continue next time. Thank you. I should also quickly mention, because some people asked last time, there is a homepage that goes along with the lecture, and here is the link. You can also take a picture of that QR code, and it will take you there. And on that homepage, you will find not only the recording of last week's lecture, but the recordings will show up after each lecture, but there will also be the slides uploaded, and these will be an extended version of the slides I'm showing here, in the sense that there will be additional, quote, bonus material Okay, the original texts that I showed you snippets of, there will be more of that in there. There will be more references and more links in case people want to explore a bit further. Any questions?
Two questions. It appears you stopped before you got to Watt's steam engine.
That will be next time. Watt's steam engine will come up next time. Yes, because he was actually very closely connected to Black.
Okay. And the other question is, various developments here are counting on the piston.
That's right.
Is, in the history of science, is there an individual or a group that developed the piston, or did it just happen?
There's many stories, and you can decide which story you want to believe. So the question was the piston. We saw Newcomen's steam engine already sort of took it for granted that there was the piston. Let me go back. Here, right, there was this metal cylinder with a top that could move up and down. This is what was a piston, and that was very central to make this entire machinery work. And the question was, who had the first idea, who had the idea first about making a piston? And there's many different stories, one of which goes as follows. There is a French person, Denis Papin, and he built a steam digester, okay, a pressure cooker. He had a metal vessel that he closed up to cook meat. That's why it's called a steam digester. It would cook meat much more rapidly, as a pressure cooker does, than normal. And in fact, he would cook for the King of England to sell his invention. That was a big thing. But the first steam digester that he built would also be prone to explosions, because what he forgot was to include a relief valve. You can imagine if that steam, got too high pressure, the thing would just blow up in his face, and that's what he forgot at the beginning. And then he would add that relief valve, okay, a little flap that would open as the steam exceeded a certain, safe pressure level. And there's the story, I have no idea to what degree it's true, that he was sitting there in his table, sort of watching the steam digester digest away, and that flap of that relief valve would sort of open and close as the steam sort of puffed out. And that, in him brought up the thought of the steam, creating motion. Okay, so that was, if you want, the first glimpse at what a piston would become eventually. Something that could create motion out of steam. Now the question, of course, is then how do you go from that simple inspiring thought of that relief valve flapping around to a real piston? And that's, again, a long and arduous story that has much more to do with engineering than it has with science. Right? So it's not clear out of which material you want to build that piston. It's not clear how to ensure that there is a good seal in between the fixed part of the piston, that moving part of the piston. And different people explore different things, and in the end, the things that worked are the things that survived. Okay, so there's various different origin stories, but again, as with the thermometer, there is no clear narrative that you could follow. It was everybody doing all the possible things at the same time type of thing.
What year was that where the flap was noticed?
I don't remember the exact year. It was, I believe, in mid 1600s, but I would have to double check. I don't remember.
Will you get into how the up and down motion of a piston is transferred into rotary motion?
Yes. Yes. So that would be a very good question. So there is a question of, if you really want to run a mill or any machinery that requires rotary motion, this up and down, doesn't do that. So you have to put something in between to convert it into rotary motion. And in fact, as we'll see next time, it was James Watt who made that. Okay, there's also a long story behind that. That's very fascinating. We'll see one side of that story. It will be James Watt's side of that story, and how he had to, again, circumvent and work around the patent that was already held by somebody else without paying license fees to him. There is, again, a lot of subtle matters involved. Yes?
You described the physician who weighed himself and the food everything he takes in, everything's that. And you're saying that there's some missing mass in there. And you say he attributes that to some kind of living energy being. So that sounds a little odd, doesn't it? And I'm wondering, is that idea pervasive at this time in science, that people are thinking, well, we destroy substance in order to make energy or do work? Is that how it's conceived?
So the question was about what I described in this physiology context, people weighing themselves and making sure that, or comparing, the quantity, the matter that they consume and the quantity they would excrete afterwards. And the question was whether people were thinking already in terms of taking sort of matter and converting that into energy in some way by, converting it into physical activity. I don't think they thought about it in the way that we do today, with sort of the modern glasses of science in the sense of matter really being destroyed and converted into energy. They viewed it much as, like on a much more mundane level, in that clearly it's not the same mass that gets out, so either that mass is somehow rearranged. Okay, you can also imagine there is liquid inside the food that you consume, and that liquid maybe he didn't weigh in the same way as the solid parts and so forth. Okay, so what that taught them is that there is something happening inside the body. It's not simply the nutrients being passed through, but they are sort of converted and rearranged into something. That's what it taught them, and that's sort of the viewpoint that started here. You also had a question.
I have two questions. One is this concept of the state of equilibrium when the different temperature substances are mixed. Is that related to the concept of entropy that I understand was developed in the 1800s in analyzing the efficiency of steam engines, but then spreads out through all of physics and even astronomy, and something I've always found horribly difficult to grasp, especially how you quantify it and turn it into a number that you can plug into
Right.
mathematics or formulas. So the question is, how are they related?
Right.
And then
Do you want me to answer that question first?
Sure.
Otherwise I will forget. So the question is, we had, seen Black observe that existence of that equilibrium, temperatures coming into alignment, regardless of what these objects are made of, if you just wait long enough. And the question was, to what degree is that connected with the idea of entropy, which is something that came up much later in the late 18 and early 1900s, which is a concept that exists in sort of the science of heat in its final manifestation, if you want. Okay? And the answer is, it's very much related. In fact, entropy is a way of explaining, in a certain sense, why this equilibrium eventually attains. Right? So Black simply observed that it does attain, and for us it's sort of common sense that eventually all the temperatures will end up being the same. But if you really ask, hang on, why does it happen? Why does it not simply go to equilibrium, then get back out of equilibrium, so that at the end, we end up with a hot mug of coffee again? Okay, that's the question that entropy much later answered conclusively. But at that point, people weren't really even asking that question. They were really making the first baby steps towards appreciating what was going on. You had another question.
So, having attended so many years of lectures here and read as much as I have, one of the things that has amazed me among a great number of physicists is their lack of knowledge, admitted, self-confessed, lack of knowledge of history of science. In fact, some will openly say, I know what the science is, but I don't know how this all, where these ideas came from, how they were developed. And I would say in contrast, your obvious knowledge of the history of science is incredible. And it seems to be equaled by your knowledge of the physics underlying it as well. And I'm just curious, as far as your background in physics and what branch of disciplines you have concentrated, and how it is that you have come to such a high degree of knowledge of the history of physics.
So the question is, I need to make sure to keep a straight face. The question is, why do I know about the things that I'm telling you about? And so there's an honest answer and an official answer. Okay, the honest answer is, because Ed asked me to give the lectures, and I had been curious about the history of physics for a very long time, but I never sort of had an excuse to really read about it. So Ed, came up with an excuse, and that's why I read about it, and that's why I know a bit about it.
And your concentration in physics?
In what sense?
Well, your background in physics itself.
Right.
You must have some area of concentration, or
Right.
and that is.
So I'm a particle physicist. This is what we'll get to see at the very end. Studying the smallest constituents of matter, even smaller than atoms and so forth. That's my day job. Let's call it.
Thank you.
Okay. Any other questions? Yes.
At some point, they realized that blood was flowing in the body. I guess back at least that's your reference.
Right.
They didn't know that a lot was going on inside the body.
Yes.
And you mentioned the word metabolism at one point. And they even would bleed people through the 1700s.
Yes.
I guess if they had temperature to reduce the temperature, so they were taking stabs in the dark about the temperature in the body and whatnot.
Right.
Maybe they were doing the wrong thing
Right.
to lower the temperature, but that's what they do at that time.
Exactly. So the question or the comment was about metabolism and blood and so forth. The blood certainly serves a certain function in the body. It circulates and such. And in fact, there's a very nice story that connects bleeding people as a way of treatment to how people came to appreciate the fact that there's a metabolism, and that is connected to another physician, Julius Meyer, who was from Germany, but he would be a doctor, so he would bleed people because this is what he did at these times. But he had sort of the good fortune of getting on a ship and traveling south. And he would also bleed the sailors on the ship when they were in tropical waters with a much higher ambient temperature. And he would find that when he was doing these bleeding exercises, that the blood going away from the heart or from the lungs and the blood coming towards the lungs would have the same color. Whereas if he would bleed people back home in Germany where it's colder, they would have different colors. Okay, that already told him, and he knew about, these colors must have something to do with, oxygen in the blood and so forth, supplying energy to the rest of the body. And he made the connection that in the tropics, where it's actually warmer, the body doesn't have to heat itself as much and therefore doesn't consume as much energy. And that's why the energy doesn't taken out of the blood, and that's why the colors are more similar than they would have otherwise been. Right? So there is a crosstalk between the temperature and the physiology. It was just not in the way that we saw, right, in sort of Galen's early writings, but it was in a much more different and much more concrete sense. Say.
I have a condition, a blood condition called hemochromatosis, which means I have too much iron in my blood, which is hereditary. In this day and age, the only way they can get rid of that iron is I have to go and give blood. I'm supposed to go once a month. I don't do it all the time. And it can affect all your organs when they first discover it. They check all the organs, so it's a serious thing. People should consult their physicians, I guess, to find out if they have it. But in this day and age, they can't give you a pill for it. They're going to get rid of your blood.
Right. Science never stops. That's what I can say. You had a question?
I was wondering if we would have time to put some of what's happening here in a bigger context. Like what were the powers that be, or the belief systems that either enhance the science or diminish the science?
Right.
Yeah. Are we going to be able to sort of talk a little bit about that? Like what was the political system or the religious system that either enhanced or diminished
Right.
what was happening?
So we're going to see some facets. So the question is about, there is certainly, I tried to give you some context, but obviously there's a lot more context. There's religion, there's politics, there's wars and such being fought. How does all of that play into science? And we're going to see some sides of that starting next time, because the science of heat was a very big topic in France And France is also known for its sort of political turmoil in the 1700s and 1800s, French Revolution and so forth. And we're going to see how that interplays, in fact. And then later on, how the First and Second World War that were very big, had very big impacts on science. We're going to see that very, very clearly. Absolutely. Okay, anybody else? Okay, if not, thanks very much.